Well, here we are in the American Ceramic Society's course on firing of ceramics. We're in Unit 2. This is about kills. In Unit 1, we talked about some of the changes happening within the ceramic. I understand that you may have taken other courses in this sequence that talk about things like sintering. But we talked in Unit 1 about vitrification, about reactive sintering, and about solid state sintering, at least to the point that we talked about changes that happen within the body itself that we are firing, the wear that we are firing. And we learned basically that whenever there's a linear change or volume change involved, that we typically will slow down the firing schedule in order to not cause cracking in the body. In Unit 2, we've advanced into kills, and so far we've been talking about gas and liquid fuels and getting them to the kill. That's through a system of devices that control the pressures and flow and provide the burners with the fuel rates and air rates that are required in order to create combustion and a stable flame in the burner so that we provide heat into the kiln. This is what I always have referred to as the plumbing section of the course. It's very important. I've talked a bit about being able to look with your eyes and tell what's going on in terms of valve positions and things of this nature, observation ports on burners that you can look in and tell that the burners are operating, about flame supervision equipment that's automatic. So we've talked about a number of things. So we basically have the air or oxidant and fuel to the burners. Today we're going to talk about burner control and burner placement in kilns. We're still talking about gas and liquid fuels. I have decided to add an X class on solid fuels. So if you're not using solid fuels, I recommend you look at the next class because we're going to talk about things like dust explosions, which you need to know something about, not with respect to ceramic powders, which are not combustible, but dust explosions happen with solid fuels because we have powders that can oxidize. So today we're going to get about the business of talking about burners, burner control, kills, and kill safety. Now, I want to speak, I've said this before, but speak to the fact that I've used many diagrams from the North American Combustion Handbook. I've always had very good relationships with North American personnel. I've used their diagrams because they've supplied things to me before for use in education. So I believe that company promotes education. And so that's the only reason that I'm using copyrighted material. However, I want to make sure that if you share these images with other colleagues, you would follow your organization's copyright policies strictly so that there are no problems. North American is a good company. I'm not promoting them. I've just had good relations with them. Now they are part of the Phoebes organization. So I wanted to mention that before I get started. Also, I want to speak to the use of PowerPoint in these lectures. I recently went to a meeting via Zoom, and the speaker said, I'm not going to use a PowerPoint because PowerPoint is neither power nor point. Well, that's his opinion, of course, and I understand that PowerPoint can get a little old. It's not the most effective education. I like standing at the marker board and talking to students as I draw. That's just not possible in a practical manner here with Zoom classes. I understand that I can have a whiteboard that I could use, but I'm choosing to use PowerPoint. And PowerPoint, to me, is a really good tool to show images and pictures. that I couldn't show otherwise, that I can't draw. So trust me, I'm not that much of an artist. So we are using PowerPoint. And the other advantage of PowerPoint is that you can review these lectures. There are a few more words than I speak on each slide. And so it's almost like a little textbook, a summary or outline of the course that you have available. And of course, you can receive these PowerPoint slides from the American Ceramic Society upon your request. So let's do a little brief review. We started the last time talking about getting the right amount of gas pressure into your plant from the supply line from the outside world. This is done with a pressure regulator. Regulators provide the proper dynamic pressure in the piping system, the gas supply system, to the burners in order to for the burners to operate properly and have a stable flame. Now, there's a difference between static pressure and dynamic pressure. Static pressure is the pressure that is taken from a port in a flowing gas system. That's the pressure against the sides of the pipe that's carrying the gas. That's what we use actually with some of our regulators. But what a main pressure regulator is doing is controlling the flow. And so last time we talked about the gas coming in, and there's a valve that opens, there's a spring here and a diaphragm that's controlling the valve position. Okay, we don't see the whole diagram in this cutaway view, but it's pushing this valve open, and the spring pressure is helping this to happen. And it also, the diaphragm can cause this valve to close more. So it throttles up and down as we may need a constant dynamic pressure in the system. So that's where you come from the main gas supply into a supply for a kiln. Now, a related ratio regulator, is the ratio regulator, and it works the same way. It's really controlling gas flow through the system, dynamic pressures through the system from left to your right. But the diaphragm in this case is driven by an impulse that creates a pressure underneath the diaphragm, and that impulse is coming from your air system. Okay, so it is a static pressure impulse. I understand that from the air system. There's a pipe coming from the air supply system that transmits that pressure down into the ratio regulator. And as we throttle the air up in volume, it's going to throttle the gas up in volume by opening this valve in a greater proportion. So the air system is driving the gas supply system, okay, by use of a ratio regulator. Now, last time we also showed a lot of components, and I'm just repeating this slide for your use. We come from a gas supply, we come across a shutoff valve, typically a ball valve. And remember, we talked about you can look at this valve and tell if it's aligned with the piping, the valve is open. If it's 90 degrees to the piping, the valve is typically closed. So that's something you can do with your eyes to see what's going on. We have the main pressure regulator. We have low and high pressure sensors in the system. And then we have a main shutoff valve, which is basically a solenoid valve. If it loses pressure, it's going to shut off. And from one of these pressure sensors, or if it loses electricity, it's going to shut off. You have to go up and manually reset it, and it's in the reset condition right here with the lever down. That means everything's okay, and you don't turn that down until your entire system is ready for you to relight the furnace if that's necessary. So going forward, Basically the main components are a ball valve to isolate the burner groups, a ratio regulator, and a gas trim valve. In the literature, North American calls this a V-port valve because of the shape of the little valve stem. That's something you adjust manually with a screwdriver in order to get the exact flow that you want into a burner or burner group. So that's what we had from last time. Pictures of products shown on the PowerPoint slide, just so that you can recognize them. And I believe last time I recommended that you trace some gas lines along furnaces that you have available to look at so you can recognize the components. You can start at the burner and work back toward the gas supply if you wish. That's what I like to do. But at any rate, you can tell what's going on. Now I'm going to talk a bit today about combustion with oil. We'll talk very briefly about it and show you some of the utilities that you have in combustion with oil. And I'm going to talk a little bit about safety with oil. I've mentioned to you that I've been inside of an oil fire before, and it took me quite a while to recover from that. I certainly don't want that to happen to anybody else. Now, in a dual fuel burner system with a dual fuel burner, we're going to have gas and air come to the burner. We're not showing the gas or air in this particular diagram, but there is an oil supply tank and a means of starting up the oil system. This oil supply may be heated. We may further heat the oil heat the lines to get to the right vaporization temperature so the oil can be vaporized to combust in the burner system. So you see a lot of the components we have before, but in this particular case, you can also see there's a continuous loop keeping the oil heated in the system as we go around the loop. And we're also taking some of that oil off into a regulator, oil pressure regulator. The same components we have, a solenoid shutoff valve, a ratio regulator with oil going into the system. So these are the main components for the oil system. It's just like the gas system. We've got to have the right pressure and the right flow for that burner to operate. Now, the North American people have a nice diagram of viscosity of oils. This is kinematic viscosity that we might measure with a cup device like a Seybolt cup. But nevertheless, here's viscosity on the vertical axis, and we have temperature on the horizontal axis. The vertical axis is a semi-logarithmic axis, and you'll see why in just a minute. That's because the viscosity follows an exponential relationship with temperature. But if you plot it on a semi-logarithmic piece of graph paper, then you have a straight line for the viscosity of oil versus temperature. And this shows various oils from light oils up to heavy oils. In this diagram, North American has given you some general ranges for pumping viscosity that is required to move the oil around in the system, recirculate the oil. And then when we get to the burners, well, we've got to be at an atomizing viscosity. So our lines might have additional heating there depending on the type of oil that you're using in order to not only pump, but also atomize the oil. Now, oil is used less in the United States as a fuel today because of environmental regulations, but it's used as a backup fuel quite a lot. And I realize that some of you may be in European locations that use a lot of liquid fuels, and so you would be aware of viscosity versus temperature for liquid fuels according to your burner requirements. This is just a cut section from the North American viewpoint. You can see a little bit better some of the viscosity on the semi-log scale versus temperature, and you can identify the oils. So of course, I hope I've convinced you that having the North American Combustion Handbook available is a very useful thing always for data. Now there's another way to get this information. It's from the Honeywell Houck eSolutions calculator. So if you open that up and go to reference and go into physical properties of gas and liquid substances and open that up, then you'll come up with a screen that lets you select the liquid fuel that you want. For my purposes, I've selected number 6 fuel oil, which is also called Bunker C fuel oil in the United States. And if you click show properties, it's going to show you various properties of this fuel oil, but that's not where I'm going. You, of course, can use the drop-down menu to pick any particular oil or a customized oil mixture if you wish in this program. But notice the Excel. So if you click on Excel there, you're going to get a screen that tells you to set up the parameters you're interested in. And so it shows that you can do an Excel chart up to a maximum temperature of 290. I've chosen 20-degree Fahrenheit increments. And so then we're going to just say make Excel. When you make Excel, you're going to get a table, and of course in 20-degree increments up to the maximum temperature they allow. Then you're going to get the kinematic viscosity. In this particular case, I've chosen feet square per second, but I believe you can choose other scales as well. And if you want to do something kind of fun, you can make a plot of this. I've chosen to plot the data on a scattergram and then connect the dots, connect the data points, and plot a line using the exponential curve fit function. And it fits pretty well. And then you, of course, can plot an equation here if you wish for viscosity. So somewhere up here, you're going to find a pumping range, and you're going to see down here what temperature you need. And then you'll see a vaporization range, and you'll see what temperature you need in order to combust that oil. Now, there are a lot of comments to make about oil safety. You know, oils have a flash point, and obviously you have to be above that flash point in order to cause flame to happen. I've shown this picture, the only image I could find that could illustrate this, which is a cooking implement with cooking oil in it, and it's flashed on the stove. So the oil has reached a temperature where it's vaporizing, and the vapor is burning. Okay, so that's the process. We have to vaporize the oil, get droplets up into the atmosphere in order for the oil to burn as a vapor. The droplets, of course, make vaporization much easier. So your oil systems, as you remember from last class, the oil burner systems have a system to inject oil into an airstream in order to create vaporization before that vapor is injected into the combustion portion of the burner. The situation I was in where I was burned was oil was being sprayed. This was a long time ago, and oil was being used as a herbicide to kill weeds. And a piece of industrial equipment had a section that was hotter than the vapor flash point of that oil mixture. This was diesel fuel that was being used. and it flashed. Unfortunately, I was in the middle of it, as were some other people when it flashed. And so you have to be very careful about injecting fuel around anything that's hotter than the flash point of the fuel, unless you want it to burn. Now, there are many other aspects of liquid fuel safety that I'm not going to touch on. You should always follow your organization's safety protocols and that of the equipment suppliers completely in all aspects to consider fuel safety, particularly when a spill might be possible. Okay, well, let's go forward. We've done gas and oil. Let's talk about adjusting the burner heat output. That's what we want to do, is to be able to throttle from a low or minimum firing rate heat release to a maximum firing rate or heat release within the kill. So we're going to focus on how you adjust it between those points. How do you place burners in a kill or large industrial furnace? How do you maximize heat distribution? And we're going to use a trademark. This is North American's trademark called StepFire. Okay, well, the simplest case of a burner is an aspirator system where the air pressure is blowing into the burner housing, and the vortex of the air, the negative pressure on the gas inlet, is causing the gas to aspirate into the burner. And so given the correct pressures, then you are using the air to drive the burner output. You're going to see a lot of this today. Why are we doing that? Well, for one thing, it's really easy to control the air with a curtain valve or some other type of valve. So here we're just injecting air into the system, and that's pulling the gas, so to speak. We use aspirator devices on things like little vacuum ports on laboratory water supply systems. Sometimes if we want a small amount of vacuum, we can use aspirator burners on low temperature combustion equipment, ovens, home devices that we use for combustion. Now, step forward in an excess air burner. Remember, an excess air burner puts out a lot of hot air into an enclosure. It's used for lower temperature ovens and furnaces. And in this case, we are controlling the gas that's going into the system. Here's a gas control valve in the system, and we're just using a lot of air. These valves are not talking to each other. They're not linked together. We manually adjust them in the one valve system to get the right fuel and air input. And so this is probably the simplest and oldest type of system with gas and air burners. If you go one step higher, we can link the air valve to the gas valve. Okay, so that means as we throttle up the air, we're going to throttle up the gas. And in that situation, even though we still have an excess air burner, remember that's the burner with the large opening on the side of the kill wall, we've linked the air and the gas together, and it's a more modern approach to controlling an excess air burner. The ultimate is the ratio cross-connected system. So here's the air system, and here's a curtain valve or butterfly valve giving air supply to the burner. So there's the air coming into the burner housing, and there's the refractory portion of the burner. But in this case, in the gas system, we've got a ratio regulator right here. And then we've got the other components of the system, a trim valve or whatever we may have in the system to give the gas supply to the burner. But the key is the static pressure impulse that's carried in a line down to the ratio regulator. So as you throttle up the air, more dynamic pressure, then we've got more static pressure on the side of the air supply line. That static pressure impulse comes down to the ratio regulator and drives the ratio regulator for the gas system. So we're using the ratio regulator to modulate up and down the amount of gas that goes in the burner, which modulates up and down the amount of heat output of the burner. Ratio cross-connected linkage. System's been around for a long time and works very well. These are very rugged components for a kiln. I've shown you the diagram before, and this is a dual fuel system. It's North American's diagram of the air supply, and you can see the air supply going over here through a curtain valve or high capacity valve. And down here, we're taking off air pulses, pressure pulses, going to the ratio regulator for the gas system or the ratio regulator for the oil system. So the gas system is shown here coming toward the burner. The oil system is coming down here in part, showing the oil supply to the burner. There's a lot of information on that diagram, and so you can pause this presentation and print it if you would like, although I'm going to show you a section of that diagram in the next portion. And there I think you can see a little bit easier. I've used the little blue arrow to show the air coming down to the burner. Of course, there's also air coming to the pilot light on the burner. Then there's an air impulse coming over. The blue arrow is coming down to the gas system. There's another impulse, blue arrow, coming down to the oil system for the ratio regulators to control either gas or oil in combustion. So that's a little easier for you to see on the PowerPoint presentation. Cross-connected ratio regulator control. The air impulse, the amount of air is driving the amount of gas that you get in the system, which means the amount of air is driving the heat into the system. A lot of people that work with kilns talk about the volume of air liberating heat in the kiln, and that's where they're coming from, because they are using air to control the amount of heat that's released in their kiln. Okay, so we're going to talk about burner placement in kilns, and burners are typically grouped together in kilns. They don't have to be, but the components that you've looked at, the ratio regulators and the trim valves and the shutoff valves, are all expensive. So we may place burners together in a group. So I'm going to show you a diagram which has three burners linked together to function as one group working together. So here's the gas coming in. There's one ratio regulator, which is driven by the air system. Here's the air coming in. Okay, there's a air valve that's controlling the amount of air going to these three burners. So if you follow the gas line, it jumps the air line and comes into a T where it's going to control or provide gas to the individual burners. Okay, so that's what's happening over here and over here. So three burners in this burner group. The air system jumps the gas line and is provided, well, I guess I had that wrong just a minute ago. It's the air system that's coming into the side of the burners. Okay, so I apologize for that. And the gas system comes up, directly. I'm going to get this right eventually. There's the gas, and here's the air system coming in. So you can follow these lines better than I can looking into a computer screen. But here, an impulse from the air system is driving the ratio regulator on the gas system. We don't show any air or gas supplies for the pilot lights on these burners, just to simplify. They do show trim valves for controlling the flow rates on the gas and air systems. Now, of course, I have to talk about the heat that's emanated from a burner. So we're showing some systems with burners spaced close together and a cone of heat emanating out from the burner port. Okay, so here's the heat coming out. And if we place them a little further apart, that cone shifts a little bit to the right. And you can see that areas between where the cone of heat is are basically space that is lower in temperature, and sometimes people like to call this dead space. So a burner has a given cone of heat, and so people space these burners apart based on what's allowable for the product that you're making for this dead space or lower temperature space not to impact the product quality. The lower diagram shows burners being directly opposed to each other, which they can be, or burners which are offset. Okay, if they're directly opposed from each other, we're going to create turbulence where the cones of heat meet. And that turbulence, because it's heat, the turbulence is going to tend to go upward toward the crown or roof of the kiln. We can offset the burners, which causes a swirl. That swirl tends to go up toward the crown. So again, the spacing here and the distance apart of the burners is all engineered to give you more uniform temperatures. Now, burners are usually arranged in a kiln to prevent flame impingement on the product. We don't want that cone of intense heat hitting directly on the product that we're firing. We want a swirl of heat. You're going to see that the heat transfer in kilns above a certain temperature, when we get into the 800 to 900 degrees Celsius range, we're going to have heat transfer by radiation from the flame and by convection. The swirl of hot gases going through and around the product really helps us to transfer heat into the product. That's what we need to do to cause sintering to take place. But nevertheless, we typically will avoid flame impingement directly on the product. So in intermittent kilns or periodic kilns, we typically will cause a swirl around the product to take place by placing the burners to encourage swirling around the load that's in the furnace. And tunnel kilns or ovens, we might do what's called an index push. So I told you I wasn't a very good artist, right? So here we have a tunnel kiln with product coming in from left to right. So this is the preheat section of the kiln. We've got burner groups up here, the hot zone of the kiln, and we've got the cooling zone of the kiln. So we typically use ambient air to cause cooling to occur. I'm going to show you some ways that we do that, and that waste heat can go over to the dryer. Nevertheless, we have burners placed at different locations and discrete kiln cars. So what happens in an index push is the burners come on and fire between the kiln cars. They don't fire directly onto the product that's stacked on the kiln cars, and fire between the units of production, the units of wear, to create heat. Whenever there is a push, we call this a continuous kiln, but it's actually pushed in increments. And so whenever the product is being pushed and going under the burner position, the burners cycle off until the product is past that position, and then the burners come back on. An index push to avoid flame impingement. Now, flame impingement not only can thermal shock the product through hot spots, it can cause reduction effects on the product. In the case of clay products, it can change their color. So nevertheless, index push is very common. Now we have side-fired versus top-fired. Side-fired kills fire typically low in the side of a kill. This is a cross-section of a tunnel kill, so the product is moving towards you or away from you in this particular diagram. And these are burners that are offset. They're not firing into each other's cone of hot air. You can see the air is tending to go upward in this furnace. And what is not shown is the third dimension, some swirling action that can occur because there's a draft down the tunnel, whichever direction draft is. So it's pulling the hot gases along the length of the tunnel as combustion takes place and as the heat rises. So we're firing at a low position on the car, trying to make sure that the units in the bottom of the setting receive the same heat treatments as those in the top of the setting. The other way to do this is directly oppose the burners, and that creates a swirling action here. Remember, this kill load is offset from where the burner flames, burner cone of heat is coming out. The other possibility is to fire from the top, and many of the newer kills fire down through the crown. And so there's a burner in the top that fires downward. And here we have two settings. These are brick examples, two settings of bricks, and we're firing down between the two settings of brick in order to create combustion and force heat downward. Of course, it's going to move through the load here, and it's going to move perhaps below the load or in front of the load right now because it's firing. These settings of brick are not directly underneath the burner. We can have these across the kill. So you're typically going to see a lot of burners in burner groups along the top of a modern tunnel kill. So we're just all here trying to set these burners in such a way as to not have flame impingement and also to push the heat down. We're fighting the buoyancy of the hot gases when the burners are firing. Now we're going to get problems in a tunnel kill of the type that I've shown in the preheat section. Okay, because here cold bricks are coming in from the left, but the air is going to want to channel toward the crown of the furnace. Here in the cooling section, we have hot bricks. We're trying to use ambient air in order to cool this wear so we can get it out of the kill. But again, as the air heats up, it's going to want to channel toward the roof of the kill. So there are some things that we do in order to try to combat this. And in the preheat section of the kill, remember that's where the bricks are cold, but the air is wanting to be hot toward the top of the crown. We can take air from the bottom of the setting and recirculate it to the top of the setting. You can see the arrows here showing that we're forcing air downward. Now these are diagrams of some sort of temperature probe, maybe traveling thermocouples that are in the setting from the bottom of the setting to the top of the setting, and they're color coded. So we noticed that in preheat we weren't getting good heat distribution. So the solution was to put in these recirculating systems on the preheat section of the kill, take hot air and blow it downward into the setting. And then the same traveling thermocouples are shown here to determine the heat distribution in preheat. The other problem area is cooling. And here we're trying to take cold air and blow it toward the bottom of the setting because we're trying to cool the wear off, in this particular case, bricks. So we're pushing air upward through the setting and collecting it and recirculating it. And so we have the same kind of situation here, thermocouple readings versus position in the cooling section from the exit end of the burning zone to the exit end of the kill. And after we put in this recirculation, we have a much more uniform amount of heat distribution. Remember that we're always slowing down as we cool through the quartz inversion, right? Or we're dealing with the cristobalite inversion and cooling, depending on what kind of product that we're making, so that we want to be able to control that rate of cooling, particularly through those inversions, slow down through those inversions. Now, traveling thermocouples are the old way of doing this, setting thermocouples on the setting on a kill car and the thermocouple wire traveling down the length of the kill so that you can garner the signal from the entrance end. That's a lot of work. And so some people have invented, this is one trade name, DataPack, where the thermocouples are put in the setting and a transmitter is put in a insulated container and placed on the bottom of the kill car so we don't have the wires traveling, and we can get a profile of temperature versus kill position. Our aim is to have the wearer all experience the same heat work, temperature, and time, regardless of position on the kill. And so you can find devices like this one in order to make sure that you have good heat balance in the kill. Now, I just have a slide because in unusual cases, sometimes you can have a significant amount of heat evolved in the entrance end of the kill, in the preheat section of the kill. One employer that I worked for used a liquid fuel as a lubricant in the product that they made. I can't reveal to you what the product is because I have a confidential disclosure agreement. It's a funny thing that agreement also bound my children and their children from ever revealing the secrets of my manufacturer. Well, I'm not an attorney, but I don't see anybody could bind my children to anything. They wouldn't be interested in this topic anyway. They're a bunch of lawyers. So nevertheless, the product that was made in that case actually caught on fire when that fuel oil ignited. The fuel oil that was in the product caught on fire, and there was visible flame in the preheat section of the kill. In another case, I visited a brick plant in France that was making bricks out of coal mining tailings that had accumulated over the years. You know, this was a recycling effort. There was no coal mining at that location anymore, but there was a mountain of tailings. So they were making brick from it, and the brick clay contained a fair amount of carbon. So once the tunnel kill was in operation, actually enough heat was evolved in this kill in order to fire the bricks completely. So the question is, how do you control that firing rate in this early section of the kill? And the answer is you control it by controlling the amount of available oxygen that's in that part of the kill, so you can slow down the combustion rate and make good product. Here's a laboratory example, and we're just measuring heat evolved in a differential scanning calorimeter versus temperature on heating. So the clay, in this case, a shale product with no coal dust added, says that you're going to require about 200 BTUs per pound. That's endothermic upward in this diagram, 200 BTUs per pound due to dehydroxylation of the clay. Remember that? Around 500 to 600 degrees Celsius, we're going to require energy because decomposition of the clay crystals is endothermic. But now start adding some coal dust. And you see two exotherms here, very common with coal, this type of coal. So there's a fairly low temperature exotherm where we get a little bit of heat, and there's a higher temperature exotherm where we get more heat. So the low temperature exotherm is the combustion of the volatiles that were in the coal, and the high temperature combustion is the combustion of the solid carbon material that's in the coal. So you can see that we were able to pick up some heat over and above that consumed in dehydroxylation. When we went up to 3% coal, you can see this typical early combustion that gave us 17 BTUs per pound of brick of clay. And then we added the higher temperature combustion of the coal at 90 BTUs per pound. Now, these are finely powdered materials in a laboratory instrument that's heating at a pretty good heating rate. Obviously, that takes longer to take place within a product. If coal was within a product of significant thickness, so as in the case of the French brick plant mining tailings from coal mining, then this heat release took place over a period of time, and they starved the kiln for oxygen in the preheat section so that they could maintain this oxidation toward the burning zone at the kiln, and used no fuel whatsoever once they had reached a steady state operation. Now I'm going to talk about combustion of solid fuels next time. I decided to go ahead and do that because there are some safety issues involved with solid fuels, and I've seen some examples of solid fuel used in, for example, the continent of Africa. And I have become aware of some health issues with solid fuels. So therefore, I want to spend a brief lecture next time on solid fuels. Won't be a long lecture. Okay, now pulse firing evolved into today's world, also called step firing, North American's trademark. So the idea is that the burner contains combustion, and combustion creates a high pressure pulse that comes out of the burner opening. So the high pressure pulse of air in what's called a high velocity burner can shoot that pulse all the way across a kill setting or across a kill dimension. And by doing this, we don't have the dead spots that we have in normal combustion. So the idea is to have a special burner, a high velocity burner that contains a lot of the combustion to create pressures that force a jet of hot air, combusted air, very high temperature air, and maybe some combustibles into the kill atmosphere to get more even heating in the kill. So we can do that basically using solenoid valves to cut off the gas supply, and we can link them to air curtain valves to cut off or minimize the air supply simultaneously. So we're only calling for air and fuel when we want it. Now, these burners can burn continuously on low fire and then pulse up to high fire, or they can be off and on, either combustion or no combustion, depending on the design of the combustion facility. So high velocity burners are required. We get better distribution of heat and better atmosphere control by using these burners. So you can walk by kill, if you hear click, 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 then you've got solenoid valves operating in the control system, and you know that you have a step fire system. So I think it's kind of cool that you can use your senses to see valve positions, and you can use your senses to see and estimate the temperature in a furnace by the glow in the furnace. Or kill, you can use your ears to tell in part. If it's a step fire system, of course, you can always hear the blower, the rather high frequency blower. So here's the control system. So the gas line is on top, feeding the burner. Here's a ratio regulator in this system. This slide was supplied to me by some good North American people, a trim valve. Okay. That's their symbol for a little manometer device. That's their trim valve symbol, and the gas is going into the system. But the gas flow from the ratio regulator is being controlled by this curtain valve that is throttling the air up and down as may be called for, depending on the design of the step fire system. So there's the control valve. This is presented as one type of system, maybe a simpler type of system using a ratio regulator. In system number 2, we've got a bypass around the ratio regulator so that we can always be supplying gas if we want to into the burner. So that's controlling the low fire situation. If we want to have low fire in the burner, it's still a ratio cross-connected system. You can see the airline, the curtain valve, or solenoid valve, or butterfly valve, and we're driving an impulse up to the ratio regulator. We have the solenoid valve here controlling the airflow, but we can get low fire here when the solenoid valve is open, and we can just control that. The next system basically eliminates the ratio regulator. So we've got an air line, and in that air line we have a solenoid valve that's controlling the air. And the gas line, we have solenoid valves, 2 of them here, controlling the air, but we have the ability to shut off the entire gas and air supply at one time. The entire gas supply at one time, or we can leave the gas supply open and we can have low fire and high fire by controlling this particular solenoid valve. We have a bypass here on the air system as well. Now, most people aren't going to let burners sit in a kiln with no air flow through the burner. The reason is that the air is cooling that burner tile, the refractory part of the burner. If you had no airflow at all through that burner, it's going to get as hot as the kiln is, and perhaps get too hot. So typically we'll maintain some minimum airflow or minimum gas and airflow through a burner system. Again, North American supplied this diagram comparing a modulated burner system, that's a ratio cross-connected system that goes up and down depending on what you want, with a step fire system. And you can see the available heat for their measurements, depending on the operating rate, is much higher. The green bar is the available heat in the system as compared to a modulated system. So the whole deal with a step fire system is to get better energy transfer and minimize fuel utilization. So we'll talk about kiln safety. The basic idea is that combustibles must always be removed prior to lighting a kiln. Now, I've been involved, at least on the periphery, a support role where there was a kill explosion. In this particular situation, there were several tunnel kills that were interrupted by a power outage, a weather-related power outage. And so after electricity was restored to the plant, the crews in the plant went to relight the kills one by one. And this takes some time. It's not easy to do with a tunnel kill, a lot of burners to make sure are functioning properly. And so when they got to the last kill, it was getting late in the day, and I suppose people were tired. In the preheat section of the kill, there were some burners where the safety system was not functional. And when they went to light that kill, the kill tunnel was partially full of gas, and the kill blew up. It blew up with two people on top of the kill working on it. They were blown into the roof of the plant and fell downward. Fortunately, both of them survived. But remember that with natural gas, you have a ideal percentage for combustion. You have a minimum combustion percentage, combustion atmosphere, air gas mixture, and you have a maximum. So whenever a kill is relit, kills are typically purged to remove flammable volatiles. Now, in your experience, this is no different than people that work on sewer systems, right? Or other areas where there may be combustible gases. Guys go into a sewer system, the first thing they do is stick a combustibles meter down into the sewer system to make sure it's safe to go down there. If it isn't, they're going to have to add appropriate amount of air so that they're below the lower flammability limits on the sewer gases that are there. Purging an enclosure to remove flammable volatiles is only appropriate. What if you went in a fuel system and used a hammer on a metal component and created a spark? And that's enough to blow up the system. So kill safety is very important. I do not intend this course to be a full review of kill safety. Kills were designed in the United States using National Fire Protection Association, NFPA regulations. Kill safety is addressed by insurance carriers. It's verified by insurance inspectors, perhaps an annual inspection business. And so all aspects of kill safety should be included in your safety protocols by your organization. Kill safety has to do with fuel spills and other topics, fuel releases within the plant, and not just purging the kill, but purging the kill is certainly something that I wanted to emphasize today. You must follow your organization's full training and safety protocols relative to any topic related to fuel safety. What I said today was not comprehensive. Okay, well, to summarize today's lecture, we talked about burner control, the ratio cross-connected systems that are rugged and have been in place for many, many years. And we talked about the newer pulse firing systems with North America's trademark being StepFire. We talked about the advantages of StepFire because we want to use our fuels in the best possible manner, most efficient manner. We talked about burner placement. We talked about flame impingement and some of the problems that go with flame impingement. We talked a lot about safety. So I think I don't need to repeat this once again, but nevertheless, I want you to look forward to the next class. I decided to do a class on solid fuels because of the safety issues. It will be a brief class. And so I will look forward to meeting with you next time. I remind you that you can contact me anytime by email, or you can pause these presentations to review things. You can review them at will, and you can request them from the American Ceramic Society. So the next class will be about solid fuels, particularly with some safety items related to solid fuels.